Hi everyone, we are going to be continuing on talking about the properties with logarithms, but today specifically to start talking about solving exponential equations by using logarithms and using properties of exponents and logarithms to solve equations in general. So the first page of the notes on page 69 talk a lot about some equations that we've seen similar functions to before. And that I've solved before, but we haven't properly introduced how this is going to work. So very similar to what we've done before here, you see that we're isolating down the logarithm as much as possible, taking the natural log of both sides, allowing us to move that exponent to the front like we talked about in the last lesson, and then finally solving for t. So they want us to kind of follow that process and use the same same process to figure out the amount of time it's going to take the account to hit this amount of money. So let's start with 120,000. So if we are looking still with the same amount of money that Jose invested initially and the average compounding continuously, our setup is going to be really similar to what it was up above, where we're having the 120,000 is what we're trying to see when that's going to equal, and our initial investment was 100,000, and compounding continuously e to the r, which was 0.065, 6.5% t. Okay, so we're going to start by isolating as much as possible our logarithm, right? The e, or the exponential, the e to the 0.065 t. So when we divide 120,000 by 100,000, we end up with 1.2. And then as we stated up above, we're going to want to take the natural log of both sides here so that we can undo this ln of e, and we're left with ln of 1.2 equals 0.065 t. And then last but not least, again, divide by that 0.065, and you should get approximately about 2.805 years. So just under 3 years, okay? And you can try that again to solve for the other values. Now, we have, if you flip the page to page 70 then, more examples similar that use this kind of idea of isolating the logarithm in order to help us solve the exponential equation. And they walk through here example B in order to do this, okay? So there's one example that you can read through to solve. And I'm going to go through a couple other examples here with you. So a reminder, just a side note that the book talks about as well, just be careful, especially if you have an older calculator with the parentheses, or for both of them, make sure you're closing your parentheses when you're correctly dividing, okay? So notice the book up here likes to use the common basis to cancel things out and rewrite it like this. I'll also talk about it kind of using a change of base way as well, okay? Now, this first problem here for part A, both of these, or notice that we have our exponential portion of this, the exponents kind of isolated as much as possible. And anything with a base 10 is good news to us because the common log, because it is base 10, will undo that. So if we do it to the left-hand side, we're going to also do it to the right-hand side. And again, a log with a base of 10 is going to cancel out that 10, and we're just left with x minus 1 equals log of 270. And then we can add 1 to both sides to get our value of x by itself. Now, this is where they were talking about you're going to want to be careful to make sure that you close your parentheses, because otherwise you're going to end up getting the wrong value here for this. So again, approximately 3.43 is going to be our answer here. Now, moving on from there, this particular problem, we are not isolated to start. So we're going to have to start by moving the -3 over using addition, and we're going to have to isolate our base of e as much as possible so that we end up with e to the x plus 1 equals 3. Now to undo that base of e, again, our friend, the natural log can be employed. we end up with x plus 1 equals ln of 3. And then finally, subtract 1 from both sides to isolate this as much as possible. Again, be very careful to close your parentheses in the calculator. And the natural log of 3 minus 1, you should get approximately 0.099. Okay. So moving on from here, though, what happens when our base isn't necessarily a log base 10 or ln, right? So again, to start, we're going to want to isolate as much as possible. Okay. Now you're going to see this done a couple different ways. The book likes to show it that you could take the log with that base of both sides. That's totally fine. I was taught, and it's also completely proper because of the change of base, to either use the common log or the natural log of both sides. So I always like to use the common log. And what happens here is we talked about that property that our exponent can move out front. So we end up with 2x out front of our logarithm. And then we still have log of 7/3 on the other side. And then careful on how you're doing your division in your calculator, but you can divide both sides by the 2 times log base 4. And our final answer then, if we type this in, we have log of 7/3. Be careful to close my parentheses. Divided by, I'm going to use parentheses to make sure my multiplication gets done correctly, 4 times the, 2 times log 4, there we go. 2 times log 4, and we end up with about 0.306, okay? Now, just as a side note though, another way you could have looked at this problem is you could have taken this, if we get to this point here where we have the isolation of our base here. Another way you might see this is taking the log of 4 of both sides, because that'll cancel this out. And then we have 2x equals log 4 of 7/3. And then all of that will need to be divided by 2. And what we're going to see is if we use our pal math alpha math, we have log 4 7/3 divided by 2, and we got the same answer, okay? So especially depending on what kind of calculator you have, these are equivalent because of the change of base formula, but it kind of depends on your personal preference and the change of base. I personally usually go with option 1, but that's because I don't personally have a calculator, like my high school calculator wasn't updated, so I had to use change of base. So, but they're equivalent mathematically. All right, last but not least, what we see here is a factoring component. So I'm going to rewrite this and say, okay, imagine that we had this as x squared minus 4x minus 5. Imagine this, right? Well, what we would do is we would factor what multiplies to be -5 adds to be -4, -5, and +1, right? We would just call this x minus 5 and x plus 1. Well, this is no different, but instead of calling this just x, we're calling it e to the x. Okay, so we're just going to replace this with e to the x and e to the x as we factor instead. So to solve them, these both equal 0. So e to the x minus 5 equals 0. E to the x plus 1 equals 0. And what we're going to notice is e to the x equals 5. And we're going to have to take the natural log of both sides to solve. E cancels out. and x is just going to equal ln of 5, which is approximately 609. Now, on the other hand, over here, when we were solving this, e to the x equals -1 when we subtract the 1 over. Well, the problem here is we cannot take the natural log of a negative number. Watch, if we try to do this, it's going to give us an error message. So be careful, because this second piece here is not possible. So we really only have this answer here of 1.609. Okay. Now, example C then on the next page is asking us to start solving, this time with logarithms in the problem. So notice they give us an example to walk through, to look at, and then they give us a couple more to practice. So very similar to the exponentials, we're going to always start by isolating our logarithm like we isolated our exponential. And to undo a log base, or natural log base, we can create it to the e. Remember, they're inverses of each other. And this cancels, and we're just left with 3x equals e to the 6. And we also are going to have to divide by the 3. So your calculator has an e to the something power by hitting second ln. So e to the 6 divided by 3. We end up with approximately 134.476. Okay. The next example then, a couple ways again you can think about this, but to undo a base of 10, or excuse me, a log base 10, we can take 10 to the log, right, because they'll undo each other. We end up with x squared equals 10 to the 10th power. And then if we square root both sides, the square root of 10 to the 10th power is 100,000. Okay. Finally, if we move on to examples C and D, again, we're going to see a couple more problems where we're going to want to start by isolating. So we're going to divide 13 by 3. And a couple ways, again, you can go about this, either using the 10 to both sides, or another way of thinking about this is, we know this is base 10. If we rewrote this, 10 to the 13/3 power equals x minus 4. And we could do 10 to the 13/3 plus 4 to get our x value. So with our calculators, 10 to the 13/3 plus 4, right, gives us our approximate answer here. Okay. Now, again, this one, kind of a viewer's choice of how you want to look at it. If you got to this point here where we had the log of x minus 4 equals 13/3, again, you could also have started this like we were doing those other problems where this canceled out. You'd still get the same process no matter how you look at it, either rewriting the logarithm as an exponential or undoing the base like this. They are equivalent to each other, just trying to give you guys options. So same idea here. I'm going to take a base of e to both sides so that we end up with the square root of x plus 2 equals e to the 7th. Well, to undo that square root, we're going to have to square each side, right? And anytime we're squaring an exponential, or an exponent, we actually end up multiplying. So e to the 14th minus 2, when we subtract that over, is quite a large number. It's well over 1 million when we're done. Okay? All right. And we have one more page of examples, okay? We're going to skip this though, so don't worry about that. We're going to then move on here to this bottom portion. Oops, do auto hide. And talk a little bit about extraneous solutions, because sometimes, kind of like we talked about in the last page with the factoring problem, we had an answer that did not work out, and that's our extraneous solutions, which you've probably touched upon in your time in Algebra 2. And that's where if you plug it back into the original equation, it doesn't work out. So you always want to double check that your answers actually work out. So when we look through example D, this is a great example of when we're going to have to use a little bit of factoring again. I noticed after we factored, we'd have two potential answers, but when we plugged the -3 back into the original, it was not possible. Thus, it was an extraneous solution, and only 2 was officially an answer. So we're going to look at a couple more examples like that, these last 3. And again, they don't really give you a great amount of room, so you may want to write this up in the margins or in another set of your notes, okay? Now, this is where those properties from the last lesson become really important, because we're going to start by condensing our logarithms as much as possible. So notice these are both log base 2, and that subtraction allows us to turn this into a division piece, okay? And then that equals 1. Now, we talked about before, officially you could do this a couple different ways. You could take the base 2 of both sides to cancel this out. I'm going to show this. I like to rewrite it as an exponential. It's the same idea, that 2 to the first is going to equal x divided by x minus 1. And then to undo this division by x minus 1, we're going to multiply both sides by x minus 1. So we end up with 2 to the first, which is just 2, times x minus 1 equals x. Distribute 2x minus 2 equals x. And if we add the 2 and subtract the x, we end up getting x to equal 2. Now, you always want to double check. Can I plug this back into the original, and will it make sense? Well, log base 2 of 2, that's going to work out, minus log base 2 of 2 minus 1, that's going to work out to be 1. And we can always, type this into the calculator and check if we need to. Okay, so here's our final answer on that one. Now, one of the biggest common problems you are going to see is one like B, because a lot of people are going to want to just cancel all of these logs out. Okay, you have to condense first. And that really goes for all of these problems, that you want to condense first. So on this left-hand side, we can combine these natural logs using multiplication because they're being added. And now that we are down to one singular logarithm on both sides, we now can cancel these out, okay? So we have x to the third minus 8x equals 8x. And if we bring all of these x's over to one side, notice we end up with minus 16x equals 0. Well, there is a greatest common factor involved here of x. So we can factor that out. And then we have a difference of 2 squares possible. Okay, so officially right now we have 3 potential answers: 0, -4, and +4. But we always need to go back to, are these extraneous solutions or not? So if we plug these back into the original, a couple of these are not going to work out, because if we try to take ln of 0, that's going to give us an error message. If we try to take ln of -4, that's going to give us an error message. So right away, because of this piece right here, in the original, it's not going to work out. It's also wouldn't work out here as well. So 0 and -4 don't work out, so our only answer ends up being 4. And again, when in doubt, you are able to test this, that ln of 4 and then plus ln of 4 squared minus 8 is in fact going to equal ln of 8 times 4. Get that same value. So we could test that the left-hand side equaled the right-hand side when in doubt. All right. And last but not least, example C is going to go back to the idea that you always need to condense first on here. So we're going to condense this right-hand side first. So we have log of x plus 5. And then the subtraction is going to work like division. So x minus 1 divided by x plus 1. Okay. Now that these are condensed and there's one log on both sides, we can cancel them out. Okay, again, notice there's a difference between letter A when there wasn't a log on both sides to cancel out, and letters B and C where we had one log on each side to cancel out. So now we have x plus 5 equals x minus 1 over x plus 1. Well, very similar to what we had to do right here in letter A. What's my mouse? In letter A, where we had to multiply both sides by that x minus 1. We're going to multiply both sides here by the x plus 1 so that they cancel out. And on the left-hand side, we can expand this so that x plus 1 times x plus 5 is x squared plus 5x plus 1x plus 5 equals x minus 1 on the other side. This guy here that we didn't lose. And then as we bring this all to one side, we have x squared plus 5x plus 6 equals 0. And what multiplies to be 6 but adds to be 5, 3 and 2. And finally, when we solve, we get answers of -3 and -2. Always, though, check for our pal, the extraneous solutions, right? Because if we try and plug -3 and -2 back in, we get -3 plus 5. Okay, that's okay, but -3 minus 1 or -3 plus 1, that's not going to work out. And then same thing with -2. On the left-hand side, we're okay. But if I try to do -2 minus 1 or -2 plus 1, those are coming out as negative answers. That's not going to work out. So fun fact, this one is no solution because both are extraneous. So all that work for us to say that they are extraneous solutions. Okay? All right, so lots and lots of information, but big vocab word here of extraneous solution today. Okay, know it's a lot to go through and solve these equations. There's a lot of examples though given throughout, and make sure when in doubt you reference back here, and any questions, make sure you let me know. Thanks, everybody.